Hello everyone. Today we are going to discuss another new concept on second modulo, that is Fourier series. Concept is half range Fourier series. Let us see what is the use of this half range Fourier series when we use the half range Fourier series. In an interval of length 2L, we have seen that in general a periodic function of x will have a Fourier expansion containing cosine terms and sine terms. This is our previous knowledge. That is, we know that the expansions Fourier series or Fourier expansion which is having sine and cosine terms when the interval is interval of length 2L. And many times it becomes necessary to have the expansion containing only sine terms or only cosine terms. Means sometimes we need to apply the expansions which is having only cosine term or sine terms on the basis of given example. For that, the function must be defined in the interval of the form 0, L. To get this expansion which is having only cosine term or sine term, we have to define the function is in the interval 0, L, which is to be regarded as a half interval. This interval can be regarded as a half interval. We then extend the definition to the another half in such a manner that the function becomes even or odd. Here also we have to distinguish the expansions, that is a sine series or sine Fourier series or sine Fourier expansion on the basis of even and odd functions, and this will result in a cosine series only or sine series only. Here we have two cases. First one for the cosine series. Consider f of x is equal to phi of x when x lies in the interval 0, L as a given interval. Next, f of x is equal to phi of a minus x in the interval minus L, 0, which we have to assume to make the f of x is even. We have to consider the given f of x is even. To make the f of x is even, we have to assume this second function, that is f of x is equal to phi of minus x in 0, minus L, 0. Next case is for sine series. Here f of x is equal to phi of x in interval 0, L as given, and we have to consider f of x is equal to minus phi of minus x in the interval minus L, 0, which we have to assume to make this f of x is odd. As we already know that if f of x is even, the coefficient bn value is 0. We know that in our first case the f of x is even, so that for the first case bn is equal to 0. Similarly, for the second case, here f of x is odd. For f of x is odd, the coefficient a0 is equal to 0, an is equal to 0. So that means for case 2, a0 is equal to 0, an is equal to 0. Then expansion for the first case and second case is, for the first case f of x is even and there bn value is 0. Therefore f of x is equal to what? F of x is equal to a0 by 2 plus summation n running from 1 to infinity an cos n pi x by L. Take this is equation 1. Here a0 is what? 2 by L, our limits from 0 to L, f of x dx, and an is 2 by L, integration from 0 to L, f of x cos n pi x by L dx. Next, for the second case, we know that for the second case f of x is odd, and in that the coefficient a0 is 0, an is 0. Therefore, our expansion or Fourier series containing only the terms containing bn. For that, f of x is equal to summation n running from 1 to infinity bn sin n pi x by L. Consider this as equation 2. Here bn is equal to what? 2 by L, integration from 0 to L, f of x sin n pi x by L into dx. The series 1 means the equation 1 which contains only cosine terms is called the cosine half range Fourier series for f of x in the interval 0, L. First equation is called cosine half range Fourier series, and the series 2 means the equation 2 which contain only sine term is called sine half range Fourier series for f of x in the interval 0, L. Note, similarly, consideration holds means that this interval is also holds good for 0, pi as it is particular when L is equal to pi. Means this interval 0, L is holds good for the interval 0, pi when we consider it as a particular case L is equal to pi. For remembering, see this table. For the interval 0, L, required series is cosine series. The Fourier series f of x is this one. The coefficients are like this, and for f of x is in the interval 0, L, cosine series f of x is equal to this one, and bn value is bn formula is this. Similarly, for the interval 0, pi, when we consider L as a pi, cosine series is a0 by 2 plus summation n running from 1 to infinity an cos n x. Means simply in place of L you have to take pi here, pi get cancelled, you will left with only nx, and a0 value, an value is this one. Similarly, for cosine series, summation n running from 1 to infinity bn sin n x. Bn where bn coefficient is equal to this one. You have to remember this box. Let us see the examples. Obtain the sine half range Fourier series of f of x which is equal to x square in the interval 0, pi, means x lies between 0 and pi here. See here we have to find the sine half range Fourier series for the function f of x is equal to x square. Solution, we know that the sine half range Fourier series of the function f of x in the interval 0, pi is, from the table, f of x is equal to, this is a sine series. Sine series means here it is a f of x is odd function, therefore here a0 value is 0, an value is 0. We get the Fourier series only the terms containing bn, n running from 1 to infinity bn sin n x, where bn is equal to what? Bn is equal to 2 by pi. In place of L we have to take pi here because L is equal to pi here. 0 to pi f of x sin nx dx. To find this Fourier series we have to find the bn value. Here we have bn is equal to 2 by pi as it is, integration from 0 to pi. F of x value is given, that is x square sine nx dx. Here to solve this integral we have to apply the Bernoullis rule. Applying Bernoullis rule, we get Bn is equal to 2 by pi. Here we have a function x square into sine nx. Consider x square as a differentiating part and this is integrating part. According to our Bernoullis rule, we have to keep differentiating part as it is. Therefore, x square is added as it is. Sine nx differentiation is not differentiation. Integration is the integration of sine nx is a minus cos nx divided by n. Then differentiation of this one is, here we have to take the negative sign. Differentiation of x square is 2x. Again integrate this one, minus as it is. Integration of cos nx is sin nx divided by n. N into n is n square, plus we have to take the alternate sign here. Differentiation of 2x is 2 only. Again integration of sin nx by n square is minus cos nx into dx. Minus minus get cancelled, it will be plus cos nx divided by n cube. Limits from 0 to pi, which is equal to 2 by pi minus x square cos nx divided by n, minus into minus, plus 2x into sin nx divided by n square, plus 2 into cos nx divided by n cube. Limits from 0 to pi. We know that when we apply upper limit and lower limit for this middle term, that is the terms containing sine, it will be 0, because sine 0 is 0, cos 0 is also 0. Here I am only applying upper limit and lower limit for first and last term. First I will apply upper and lower limit for the first term, and after that upper and lower limit for this one. This is 0. Bn is equal to 2 by pi. I will take here minus 1 by n, which is a constant outside this limits. It will be, first apply the upper limit, pi square minus, pi square into cos n pi, minus upper limit minus x is 0, 0 into something is again 0. For the first term, upper limit and lower limit is over. The second term itself, it is 0. Next is here 2 by n cube is a constant. Apply both upper limit and lower limit for this one. It will be 2 by n cube I am taking outside. Apply the upper limit, it is a cos n pi minus cos 0 value is 1. Here you have to complete this bracket. Next one is Bn is equal to 2 by pi. It is minus pi square. Cos n pi value is minus 1 raised to n divided by n square. This is a plus. It will be cos n pi value is minus 1 raised to n, minus 1 raised to n. 2 into minus 1 raised to n divided by n cube, plus into minus, minus 2 divided by n cube it is. I will let the last equation once again. Here it is n, not n square, it is 1 because n here, because for the first time it is only 1 by n here. I am writing that expressions once again. Now solve. Bn is equal to 2 by pi as it is. It is, see here minus 1 raised to n. Here another minus 1 is there. It will be pi into minus 1 raised to n plus 1 divided by, it is not pi, this is pi square, divided by n plus, take 2 by n cube common, it will be minus 1 raised to n minus 1. Here I will take the flower bracket only, which is equal to 2 divided by pi square into minus 1 raised to n plus 1 divided by n. In these two terms, here this is a positive term, this is negative. I will take negative common in this two term. It will be minus 2 divided by n cube. Therefore, 1 will be positive, minus of minus 1 raised to n. This is the Bn. Now, thus, the required sine half range Fourier series is f of x is equal to summation n running from 1 to infinity 2 by pi into pi square into minus 1 raised to n plus 1 divided by n minus 2 by n cube into 1 minus of minus 1 raised to n into sine n x. This is the required sine half range Fourier series for the given function f of x, where f of x is equal to x square. Second example, expand f of x is equal to 2x minus 1 as a cosine half range Fourier series in x lies between 0 and 1, comparing the given interval 0, 1 with the interval 0, L. Because our half range Fourier series interval is 0, L, we have to compare the given interval with the interval 0, L. From that we know that L is equal to 1. The corresponding cosine half range Fourier series is given by f of x is equal to a0 by 2 plus summation n running from 1 to infinity a n cos n pi x by L is there. Here L value is 1. You are not necessary to write this 1. Just I am writing to conclude you that L is equal to 1 here, where a0 is equal to 2 by 1 integration from 0 to 1 f of x dx, and an is equal to 2 by L means it is 2 by 1 integration from 0 to 1 f of x cos n pi x by 1 means it is only cos n pi x dx. First we have to find the a0 here. a0 is equal to what? 2 by 1 is 2 integration from 0 to 1 f of x dx, which is equal to 2 into integration from 0 to 1 f of x is 2x minus 1 into dx, which is equal to 2 into 2 as it is. Integration of this one is x square by 2 minus x limits from 0 to 1. Here 2 get cancelled. 2 into x square minus x limits from 0 to 1, which is equal to, first apply upper limit for this one and lower limit. It will be 1 square minus 0 minus of 1 minus 0, which is equal to 2 into 1 minus 1, which is equal to 0. Therefore, a0 is equal to 0. Next is an. an is equal to 2 into integration from 0 to 1 f of x cos n pi x dx, which is equal to 2 into integration from 0 to 1 2x minus 1 cos n pi x dx. Now to solve this one, we have to apply the Bernoullis rule. Applying Bernoullis rule, we get, consider 2x minus 1 as differentiating part and cos n pi x as integrating part. Keep 2x minus 1 as it is, integrate cos n pi, it is sin n pi x divided by n pi, minus differentiation of 1 is 0, differentiation of 2x is 2. Next integration of this one is minus, it will be cos n pi x divided by n pi into n pi will be n square, it is pi square, limits from 0 to 1, which is equal to 2 into 2x minus 1 sin n pi x divided by n pi, minus into minus, plus 2 cos n pi x divided by n square pi square, limits from 0 to 1. First I will apply upper limit and lower limit for the first term, after that the second term. Here in this term take 1 divided by n into pi outside. First apply the upper limit, it will be what? Here it is 2 into 1 means it is 2 minus 1 sin n pi, x value is 1 means it is a sin n pi, minus, here I will take, okay, upper limit is over. Next lower limit is sin, when x is 0 it is 0, minus of minus 1 into it sin 0 means it is x, means x is 0 means it is sin 0, sin 0 is 0. Okay, upper limit and lower limit for the first term is over, plus I will apply upper limit and lower limit for the second term. I will take here 2 divided by n square pi square outside, since they are constant. Apply upper limit and lower limit for this one, it will be cos n pi when x is 1, minus lower limit when x is 0 it will be cos 0, cos 0 value is 1. Now which is equal to 2 into sin pi value is 0, means 0 into 0 into something is 0, and it is also 0, therefore first term is 0, plus 2 divided by n square pi square, cos n pi value is minus 1 raised to n minus 1, which is equal to 4 divided by n square pi square into minus 1 raised to n minus 1. We will take this negative sign, outside will be minus 4, I will take minus sign common, in this two term it will be n square pi square, because I have to write the constant term first, the term containing the power n as next it will be minus of minus 1 raised to n. Therefore a naught is equal to what? Minus 4 divided by n square pi square minus of 1 minus of minus 1 raised to n. Thus the required cosine half range Fourier series is given by f of x is equal to, since a naught value is 0, therefore a naught by 2 value is also 0, therefore it is summation n running from 1 to infinity minus 4 divided by n square pi square minus of minus 1 minus of minus 1 raised to n into cos n pi x. This is the required cosine half range Fourier series. Like this you have to solve the examples in half range Fourier series.